Monoidal categories and their representations, Lecture 14, Cell Modules. We start by making a parallel for the content of this lecture with positively based algebras. Let A be an associative algebra over the real numbers. Let bold A be a fixed basis of A. It consists of elements A sub I, where I goes through some indexing set I. Since we have chosen a basis in our algebra A, we can define the structure constants for our algebra in the following way. So if we multiply the basis element AI with the basis element AJ, we can write the outcome as a sum over our basis, indexed by k, of the basis element AK with the coefficient gamma ijk. So this coefficient gamma ijk, it's a real number, and this is a structure constant for our basis. We assume that our basis is positive in the sense that all structure constants are non-negative real numbers. In this case, we can define the following partial orders on the set indexing our basis. Or alternatively, we can think of this as a partial order on our basis bold A. So we define k to be left greater than or equal than j if there is an I such that the structure constant gamma ijk is greater than 0. In other words, if ak appears with a non-zero coefficient in the decomposition of aj multiplied on the left with something, with some ai. Similarly, k is right greater than or equal to I if there is a j such that gamma ijk is greater than 0. So if and only if ak appears with a non-zero coefficient in ai multiplied on the right with some aj. And k is two-sided greater than or equal to j. The corresponding notation is greater than or equal sub capital J. If and only if there is an I such that I is left greater than or equal to j and k is right greater than or equal to I. So this defines partial pre-orders on our set I, and the corresponding equivalence classes are called cells. So we have left cells, so k is left equivalent to j if and only if k is left greater than or equal to j, and j is left greater than or equal to k. Then we have right cells, k is right equivalent to I if and only if k is right greater than or equal to I, and I is right greater than or equal to k. And we have the two-sided cells. K is two-sided equivalent to j if and only if it is two-sided greater than or equal to j, and j is two-sided greater than or equal to k. So for example, if G is a group, and we take the algebra A to be the group algebra of G, and we let our basis bold A to be the standard basis consisting of the group elements, then this basis is positive, the structure constants are 0, 1, and it is a unique left, right, and two-sided cell. So all orders in this example are full relations. Now we can define cell modules for positively based algebras. So let L be a fixed left cell for some positively based algebra. Consider M the linear span of all basis elements AI such that the index I is left greater than or equal to our fixed left cell L. Then, of course, M is a submodule of the left regular module A. Denote by N the linear span of all basis elements AI such that I is left strictly greater than our fixed left cell L. Then, of course, N is a submodule of M. The quotient of M modulo N is called the cell module, which corresponds to our fixed left cell L. For example, if we take the example from the previous slide, where A is the real group algebra of some group G with respect to the standard basis, then there is only one left cell, namely the whole basis, consisting of all group elements in G, and the corresponding cell module is just the left regular A module. Also note that directly from the definition, it follows that the classes of AI plus N, where I runs through our left cell L, these classes form a basis in the cell module. So this is the basic intuition, and now let us go to the representations of monoidal categories. So here is the setup. Let's see be a monoidal category with a fixed tensor product, identity element, associator, and the two unitars. We assume that C is finitary, which means that it is k-linear over some field k, and the tensor product is k bilinear. That this category is additive and idempotent split with finitely many indecomposable objects, and that all Hom spaces are finite dimensional over K. A typical example of a finitary category is the category of all finite dimensional K vector spaces. The running example for today's lecture will be the category of projective bimodules over the dual numbers. So we have the algebra D of dual numbers. This is a quotient of the polynomial algebra in X modulo the ideal generated by X squared. And we denote by Carly D the additive closure inside the monoidal category of all finite dimensional DD bimodules generated by the regular bimodule D and the projective DD bimodule D tensored over K with D. So the indecomposable objects in this example, up to isomorphism of course, are exactly the regular DD bimodule D and the indecomposable projective DD bimodule D tensored over K with D. So here it is important that D is a local algebra, so this bimodule is indeed indecomposable. Note that the tensor product over D of the projective bimodule D tensor over KD with itself is isomorphic to the direct sum of this projective bimodule with itself. Okay, so this is our running example. Let us now recall the notion of cells in the setup of monoidal categories. Let X and Y be two indecomposable objects in C. Recall that X is left greater than or equal to Y if and only if X appears with a non-zero multiplicity in the tensor product of Y with some object M, where M is on the left of Y. Then X is right greater than or equal to Y. Similarly, if X appears with a non-zero multiplicity in the tensor product of Y with some object N, but now N is on the right. And X is two-sided greater than or equal to Y if and only if X appears with a non-zero multiplicity in some tensor product of the form M tensor Y tensor N. Up to isomorphism, this is well defined in a monoidal category. And we also have the natural notion of cells. Two elements are left equivalent if and only if each of them is left greater than or equal to the other element. So left equivalence classes are left cells. Similarly, right equivalence classes are right cells. X and Y are right equivalent if and only if each of them is right greater than or equal to the other element. And we also have two-sided cells. X is two-sided equivalent to Y if and only if X is two-sided greater than or equal to Y, and Y is two-sided greater than or equal to X. For example, in our running example of the category Carly D, we have two indecomposable objects, the regular bimodule D and the projective bimodule D tensor over KD. Each of these objects forms a left, a right, and a two-sided cell on its own. Clearly, the projective bimodule is left strictly bigger than the regular bimodule. It is also right strictly bigger than the regular bimodule, and it is also two-sided strictly bigger than the regular bimodule. This is explained by the isomorphism on the previous slide, that tensor in the projective bimodule with itself, we will get just two copies of this projective bimodule. So we cannot get the identity bimodule back. Now let us define cell modules over monoidal categories. Let L be a left cell of C. Consider the left regular C module C. Let M be the additive closure in C of all indecomposable objects which are left greater than or equal to our fixed left cell L. Then M is clearly a submodule of the left regular C module. Lemma: the C module M has a unique maximal C-stable ideal. We will prove this lemma on the next slide. We note that this ideal I contains the identity morphisms on all objects which are strictly left greater than our left cell L. So if we consider all such objects and take their additive closure, then that additive closure generates obviously a C-stable ideal, which is different from our module M. Definition: the C module given by taking our module M and factoring out this unique maximal C-stable ideal I is called the cell module corresponding to our left cell L, and it is denoted by bold C with lower index L. This is the main definition for today's lecture. Now let us prove the lemma. So proof of the lemma: we need to prove that our module M has a unique maximal C-stable ideal. So let J be a C-stable ideal of M. Assume that J contains the identity on some element X in L. Then we can apply C, so we tensor X with anything in C on the left, and in this way we can obtain as direct summands all indecomposable objects Y which are left greater than or equal to L. So this means that our ideal J contains the identity on all indecomposable objects in M, and so J is equal to M. In other words, if J is a proper C-stable ideal, then it does not contain any identity morphism on any object in our left cell L. So if we have an object X in our left cell L, then its endomorphism algebra is local because X is an indecomposable object. And in any local algebra, the sum of proper ideals is proper. So JXX is an ideal of the endomorphism algebra of X. Since it doesn't contain the identities, it's a proper ideal. And so, if we take as I the sum of all proper C-stable ideals of M, by this argument, this sum cannot contain the identity for any object X in L. And so it will be a proper C-stable ideal of M. This proves our lemma. Now let us discuss our running example in more detail. So consider our running example of the monoidal category curly D of projective bimodules over the dual numbers. We have two indecomposable objects in this example: the regular bimodule, which we denote by I, the identity object, and the indecomposable projective bimodule, which we denote by F. Let us first describe homomorphism between these indecomposable objects. So the endomorphisms of the identity are two-dimensional. We have two linearly independent endomorphisms given by sending the generator 1 of the regular bimodule to either 1 or X. So for the regular bimodule, the endomorphism is just the center of the algebra, but our algebra is commutative, so it is the algebra, the whole center. Next, we describe bimodule homomorphisms from the identity to F. So we can start with 1, and we should send it to any element in F on which the left and the right actions coincide. It is easy to check that there are two linearly independent such elements. One of them is X tensor X, and the other one is 1 tensor X plus X tensor 1. Conversely, for bimodule homomorphisms from the projective bimodule to the identity, we can send the generator 1 tensor 1 of the projective bimodule since it's projective to anything in the identity bimodule. So we have two linearly independent maps which are given by taking the image to be 1 or X. And finally, for the endomorphisms of the projective bimodule, again we can send 1 tensor 1 to anything in the projective bimodule. So as four linearly independent elements in the image, we just take a basis of the projective bimodule The standard basis is given by 1 tensor 1, 1 tensor x tensor 1, and x tensor x. So here we record the dimensions of these Hom spaces. We have the two-dimensional space of homomorphisms from the identity to the identity, from the identity to F, and from F to the identity. And we have four-dimensional space of homomorphisms from F to F. As we have already mentioned, in this case, we have two left cells. Let's take the first left cell L, which consists of the identity object. Then the indecomposables which are left greater than or equal to the identity are the identity and F. And so our module M is the whole left regular D module D. We know already, as we discussed, that the ideal I contains the identity on anything which is strictly left greater than L. So it must contain the identity on F. So the question is whether I is generated by this identity on F or it contains more than just what is generated by the identity on F. So the question is what kind of the endomorphism algebra of the identity belongs to I. So we have the two-dimensional endomorphism space of the identity. We can send 1 to either 1 or x. And the claim is that the endomorphism of the identity, which sends 1 to x, actually factors through f. Indeed, we have the map from the identity to f, which sends 1 to 1 tensor x plus x tensor 1. And we have a map from f to the identity, which is the multiplication map, which sends 1 tensor 1 to 1. Under the multiplication map, the element 1 tensor x plus x tensor 1 is sent to 1 times x plus x times 1, which is 2x. So the map which sends 1 to 2x factors through f. We can divide by 2, so we get that the endomorphism sending 1 to x factors through f. So this shows that the ideal I is generated by the identity on f, and that when we factor out that ideal, the endomorphism of I in the quotient will be just the field. So it was two-dimensional, one dimension is killed by factoring out. What remains is only one dimension. So in the quotient by I, we have one indecomposable object, which is the identity, with the trivial endomorphism ring. This means that the cell representation, the action of D on M modulo I, is actually an action of D on K mod. So this quotient category is equivalent to K mod. So it's an action of D on vector spaces. And in this action, the identity object I acts as the identity, and the projective bimodule F acts as 0. Okay, so this was about the first left cell. We have another left cell which is given by the projective bimodule F. So let's take the left cell given by this projective bimodule. Then the only indecomposables which are left greater than or equal to F is just F. So M, our D module M, is actually the action of D on the additive closure of F. It's a submodule of the left regular D module. In this case, we know that the maximal ideal cannot contain the identity on F. So it's some proper ideal of our additive category M. Note that the endomorphism algebra of our projective bimodule F is isomorphic to the algebra D op tensor over KD. So as a module, M is D tensor over KD. If we take the endomorphism algebra, we will get D op tensor over KD. Our ideal should be stable under tensoring with F on the left. And tensoring with F on the left cannot affect the right part of the endomorphism of F. So we have D tensor over KD, this is F, we have an endomorphism, and the image of the generator has a left part and the right part. And now if we tensor this image with anything on the left, the right part is not changed. So it is very natural to guess that our ideal I is generated by those endomorphisms of F which send the generator 1 tensor 1 to either 1 tensor x or x tensor x. In other words, the right part in the image of 1 tensor 1 of our endomorphism belongs to the unique maximal ideal of our algebra D, which is here on the right. So this unique maximal ideal is generated by X. So this is what we guess. Let us prove this. So let us denote by I tilde the D-stable ideal of M, which is generated by the two endomorphisms of F that send 1 tensor 1 to 1 tensor X and X tensor X, respectively. So clearly, I tilde belongs to I, because if we tensor this on the left, we cannot change this X. So this generates a proper ideal which is stable under the tensoring with D on the left. If we assume that I tilde is different from I, then I tilde will be strictly smaller than I. By definition, I tilde consists of all endomorphisms where the right part of the image of 1 tensor 1 is X. This means that I should contain more, so IFF should contain some morphism phi, such that the image of 1 tensor 1 after phi has either 1 tensor 1 or X tensor 1 with a non-zero coefficient. And now if we tensor this with something on the left, we can have this 1 on the right, and we can tensor with something which has 1 on the left. So by projecting onto suitable direct summand of the image of such endomorphism, we can get the identity map on F as an element in our ideal. And this is of course a contradiction because I cannot contain the identity on F. Consequently, I coincides with I tilde, which means that in the quotient of M by I, if we take the endomorphism algebra of F, this is the quotient of D op tensor KD modulo the ideal, which is given by the elements 1 tensor X and X tensor X. So this kills the radical of the right-hand side. So the right-hand side disappears, it becomes a field, which means that the endomorphism algebra of F in the quotient is just D op. Well, D is commutative, so it's just D. So the question is, do we know any category with one indecomposable object whose endomorphism algebra is D op and on which D naturally acts? And the answer is yes. We know such category. It's a category of projective D modules. So a very natural guess should be that our cell representation for this left cell consisting of F should be the natural action of D on the category of projective modules over the dual numbers. So in order to prove this, we need to make a detour to Yoneda lemma. So let's C be a monoidal category and M be a module category over C. Yoneda lemma asserts the following. If we take the category of all morphisms from the left regular C module C to M, this category is equivalent to the category M. So the classical analogy of this statement is the following statement that if A is an algebra and M any A module, then the space of all A homomorphism from the left regular A module to M is isomorphic to the module M. So we can take the identity in A and send it to any element in M, and this uniquely extends to a homomorphism. Similarly, for the Yoneda lemma, the equivalence between the category of all morphisms from the left regular module C to M and the category M is given by sending a morphism phi from the left-hand side to its value at the identity object in C. So this is an element on the right-hand side. Indeed, if we have any object M in M, then we can map X in C to X acting on M, and we can map any homomorphism F from X to Y to this homomorphism acting on M. And this defines a morphism from the left regular module to M. And now if we use the condition that we are talking about morphisms of left C modules, so the elements here should intertwine the C action on the left-hand side and on the right-hand side. So this condition simply implies that any morphism from C to M is of this form up to an invertible modification. And also that all modifications are uniquely determined by their values on the image of the identity object. And this completes the proof of Yoneda lemma. So now we can return to our running example and try to prove our guess that the cell module, which corresponds to the left cell of the projective bimodule F, this cell module is equivalent to the action of our category D on the category of projective modules over the dual numbers. So how can we prove this? Let us denote by bold N the representation given by the action of D on the category of projective modules over the dual numbers. We need to construct a morphism of representations from the cell module to N. So let us use the Yoneda lemma to construct a morphism from the left regular D module to N. So Yoneda lemma allows us to take a left regular D module and map it wherever we want. So let us denote by bold K the D module, which is given by the natural action of our category Carly D on the category of all finite dimensional modules over the dual numbers. So the action is given by tensor product on the left, because Carly D consists of certain bimodules over the dual numbers. Let M be the simple D module. By Yoneda lemma, there is a morphism phi from the left regular D module D to K, which sends the identity object to M. So this morphism sends the object X in D to X tensor over D M. Let's do the following computation. Let's take the projective DD bimodule D tensor KD and tensor it over D with M. We can move the brackets to the right hand side, so we get D tensor over K with D tensor over D with M. So D tensor over D with M is of course M, so we get D tensor over K M. But M is a simple module, it's one-dimensional, so it's just K as a K action, so as a left module, this is isomorphic to D. So this means that our functor phi sends the object F to the indecomposable projective D module D. So in particular, our module bold M, this is given by the additive closure of F, is definitely sent to the category of projective D modules. Therefore, our morphism phi induces a morphism which we denote by psi from M to N. So the question is, what is the kernel of psi? Whatever the kernel of psi is, it must be contained in our maximal left stable ideal I, because that one is maximal. So the kernel of psi is contained in I. If the kernel of psi would be strictly smaller than I, then the dimension of the endomorphism algebra of psi of F would be strictly larger than the dimension of the endomorphism algebra of F in the category M quotient by I. But in both cases, the dimension is 2. Therefore, it follows that the kernel of psi is equal to I, so psi factors through M modulo I, and hence induces an equivalence between the cell module and the module N. And this completes the proof of our running example. So the second cell module is just given by the natural action of our category Carly D on the category of projective modules over the dual numbers. Now let us define the action preorder. So let C be a finitary monoidal category over some field K, and let M be a finitary C module category. Then the category M is equivalent to the category of projective modules over some finite dimensional associative K algebra A, and we can list all indecomposable objects in M up to isomorphism. Let them be M1, M2, and so on, Mk. Let us denote by Mi, right arrow Mj, the following fact, that Mj is a summand of Mi tensored upon it by some object x in C. So we can go from Mi by arrow to Mj if we can act on Mi by some object in C and get Mj as a direct summand. Then this relation right arrow is obviously a partial preorder. So for example, if we take as M the left regular representation of C, then this relation of right arrow is equivalent to the relation of being left greater than or equal to. So this is equivalent to the left order on our indecomposable objects in C. If we take as M the cell module given by some left cell L, then the arrow relation is a full relation, because all indecomposables in CL, they form an equivalence class with respect to the left order. So if you start from any indecomposable and tensor on the left with something in C, we can get any other indecomposable from the same left cell. We can use this relation arrow to define transitive modules. So let C be a finitary monoidal category and M a finitary C module category. Definition: we will say that M is transitive provided that the arrow relation is a full relation for this M. This means that starting from any indecomposable object in M, we can get any other indecomposable object in M as a summand of something in S applied to our fixed indecomposable in M. For example, we just gave an example which efficiently says that every cell module is transitive. Another example, if we take the left regular C module, this is usually not transitive. Indeed, the left regular C module is transitive if and only if C has a unique left cell. Now let us define the notion of a simple module category. Let C be a finitary monoidal category, and let M be a finitary C module category. Definition: the module category M is called simple provided that it is non-zero, and the only C-stable ideals of M are the zero ideal and the whole category M. For example, every cell module is simple by definition. In the definition of the cell module, we factored out a unique maximal C-stable ideal. So the outcome, of course, doesn't have any C-stable ideals anymore. Another example, the left regular D module is not simple because we have two indecomposable objects in the left regular D module, the regular DD bimodule and the projective DD bimodule. And the additive closure of the projective DD bimodule, it is stable with respect to the left tensoring with objects in D, and so it generates a proper C-stable ideal. Example 3, if we consider the left regular module over the monoidal category of all finite dimensional K vector spaces, this left regular module is simple because it coincides with the unique cell module for this monoidal category. So in this case, for this monoidal category, the left regular module is in fact simple. Proposition: every simple module is transitive. Proof: we will prove that each module that is not transitive is not simple. So let us assume that M is not transitive. Then the error relation is not the full relation, so there exist indecomposables M and N in M such that M is not in the error relation to N. So in particular, N doesn't belong to the additive closure of the category C acting on our module M. The ideal generated by the latter additive closure is obviously non-zero because it contains M, and it is C-stable because we acted on M by the whole C. So this is a C-stable ideal, and this ideal doesn't contain M. So it's a proper C-stable ideal, which means that M is not transitive. And so the historic terminology for the notion of a simple module is a simple transitive module. So it's a little bit redundant, but this is a historic terminology. And indeed, any transitive module has a unique simple quotient. So we prove the following proposition: a transitive module has a unique maximal C-stable ideal, and hence a unique simple quotient. Proof: let M be a transitive module category over C, and let I be a C-stable ideal of M, which is different from M. Let M be an indecomposable object in this module category. Then I doesn't contain the identity on M, because if I would contain the identity on M, we could act on M by C on the left, and then we can get all other indecomposables as direct summons because of the transitivity of M, and then go into direct summons, we would get that I contain the identity on any indecomposable object in our category M. But then it contains the identity on any object, and so it coincides with M. And this contradicts our assumptions that I is different from M. So therefore, I doesn't contain the identity on any indecomposable, but this means that the endomorphism part of M belonging to I is in the radical of the local algebra of the endomorphisms of M in Carly M. And of course, if we take the sum over all such I of subspaces belonging to the radical, we stay in the radical. And this means if we take the sum of all such ideals, we get a unique maximal C-stable ideal. And this proves our proposition. So here's an example which shows that not all transitive modules are simple. So let's take as C the monoidal categories of all finite-dimensional K vector spaces. Consider the algebra D of dual numbers, and of course it's an algebra, so it's an algebra object in the category C. And so the category of all projective modules over this algebra object in C, as we described, this has a natural structure of a left C module category. Since D is a local algebra, there is only one indecomposable projective, and so this C module category is transitive, because if we have one indecomposable object, then transitivity is obvious. However, the endomorphism algebra of this indecomposable object is not trivial, because the endomorphism algebra is just the algebra of dual numbers, which is not a simple algebra over K. And so the radical of this module category is obviously stable under the action of C, because the only indecomposable is C is the identity, so it preserves, the action of the identity preserves the radical. So this means that we have an ideal which is stable under the action of C. This ideal is not zero, is not the whole thing, and which means that our transitive module is not simple. So here's an example of a transitive module that is not simple. The discussion in this lecture brings us to the following natural problem. If we have a finitary monoidal category C, classify all simple transitive finitary C module categories up to equivalence. So here are two examples where this is solved. We will discuss them in some detail later. So for the category of K vector spaces, the left regular C module is the unique simple transitive C module. For the category Carly D of projective bimodules over the dual numbers, the two cell modules which we constructed during the lecture are the only simple transitive modules. And the proof in this case is really not very obvious. It can be found in one of my papers with Vanessa Minitz. For a general finitary category C, this classification problem is usually wide open, especially if C is not rigid. There are many more examples of rigid categories for which one can solve this kind of problem. Note that the category of projective bimodules over the dual numbers is, in fact, rigid. Also, it is interesting to note that there are examples where the number of simple transitive modules up to isomorphism is infinite, which is very surprising. So let us finish with some problems and questions. Question 1. Prove that K is two-sided greater than or equal to J if and only if there is I such that I is right greater than or equal to J and K is left greater than or equal to I. Question 2. Relate cells in C with cells in the split Grothendieck ring of C when we extend the scalars to the real numbers. Question 3. Spell out all the details in the argument which we used in one of the proofs, that tensoring with the identity of f on the left and projecting onto a suitable direct summand, we get that identity on f belongs to our ideal I. Question 4. Prove Yoneda lemma with all details. Question 5. Consider with all details an alternative to our running example by substituting the dual numbers with the algebra kx modulo x to the power 3. Thank you very much and see you next time.